In this lecture, we're going to be looking at how to obtain what are called marginal distributions from joint distributions. Now, in previous lectures, we've looked at the joint distribution of two random variables. Those results generalize to the joint distributions of more than two random variables. In many situations, we're not interested in the full complement of random variables, but we're interested in a strict subset of the random variables that we have the joint distribution for. The distribution of such a strict subset of random variables, when obtained from the joint distribution of the larger set of random variables, is called the marginal distribution of that strict subset of random variables. Now, in this section and in this course, we're going to be focusing on joint distributions for two random variables, and from such a joint distribution, obtaining the marginal distribution of one of the random variables. Let x1 and x2 be discrete random variables with joint PMF, given by lowercase f. The PMF of x1 alone can be obtained from the joint PMF by summing over the space of x2. If we denote the PMF of x1 alone by f sub 1, then this PMF of x1 can be obtained from the joint PMF by summing the expression for the joint PMF over all values of x2 in the sample space of x2. Similarly, the PMF of x2 alone, which we're going to denote by f sub 2, can be obtained from the joint PMF by summing it over the space of x1. So the PMF of x2 alone is obtained from the joint PMF of x1 and x2 by summing that joint PMF over all values of x1 in the space of x1. Now, in order to distinguish these PMFs from the joint PMF from which they're obtained, we call f1 and f sub 2 the marginal PMFs of x1 and x2 respectively. So to obtain the marginal PMF of x1, we sum the joint PMF over all values of x2 in the space of x2. Likewise, to derive the marginal PMF of x2, we sum the joint PMF over all values of x1 in the sample space of x1. Now, if x1 and x2 are continuous random variables with joint PDF, again denoted by lowercase f, then their marginal PDFs are obtained not by summation but via integration. And so to obtain the marginal PDF of x1, we integrate the joint PDF with respect to x2 over the entire real line. And to obtain the marginal PDF of x2, we integrate the joint PDF with respect to x1 over the entire real line. So the marginal PDF of x1 is obtained by integrating the joint PDF with respect to x2 over the space of x2. The marginal PDF of x2 is obtained by integrating the joint PDF with respect to x1 over the space of x1. So when we want the marginal PDF of a particular variable, we integrate the joint PDF with respect to the other variable or variables that we're not interested in. And if we have discrete random variables, a similar statement applies. If we want the marginal PMF of a particular variable, then we sum up the joint PMF over the values, over the other variables that we're not interested in. So it's a very simple concept, and it's fairly straightforward, at least conceptually. And obtaining a marginal PMF or PDF of a particular random variable allows us to focus on the distribution of such a random variable and how it behaves. So let's look at some examples. So this is example 48. So consider again the experiment of tossing two fair dice and recording the up faces. Let x1 and x2 be the minimum and maximum numbers showing, respectively. Let lowercase f be the joint PMF of x1 and x2, which we have worked with and found in a previous example. So what we want to do here, now that we have the joint PMF, we want to find the marginal PDF and we should say the marginal PMF, the marginal PMF and CDF of x1. We want to find the mean, the variance, the skewness, and the kurtosis for the marginal distribution of x1. We also want to find the marginal PMF and CDF of x2, and then find the mean, variance, skewness coefficient, and kurtosis of the distribution, of the marginal distribution of x2. So let's first find the marginal PMF of x1. So recall from example 44 that the joint PMF of the bivariate random variable x1, x2, that ordered pair of random variables, is given by the following expression. The joint PMF evaluates to, or is equal to 2 over 36 for values of x1 and x2 in the sample space of that bivariate random variable, where, specifically, x1 is less than x2. And the PMF evaluates to 1 over 36 for values of x1 and x2 in the sample space of that bivariate random variable, specifically where x1 is equal to x2. And then for any other values of x1 and x2, the PMF evaluates to 0. So denote the marginal PMF of x1 by f sub 1 and the space of x1 by script A sub x1. And note that the sample space of x1 is the set of integers 1 through 6. Now, the marginal PMF of x1 can be obtained from the joint PMF of x1 and x2 in the following way. So we need to first fix x1 in the sample space of x1. Then, for that particular value of x1, the marginal PMF of x1 is obtained by summing the joint PMF over the values of x2 in the sample space of x2, which are the values 1 through 6. Now I'm going to decompose this sum of the joint PMF into two pieces. The first piece is the sum of the joint PMF, where x2 goes from 1 up to x sub 1 minus 1. And then the second piece is the sum of the joint PMF, where x2 starts at x1 and then goes up to 6. Now, the reason that this is helpful is because in this first summation, the values of x2 are strictly less than x1. And for such points, the joint PMF evaluates to 0. And so we're left with the sum of the joint PMF, x going from x2 going from x1, whatever that is, up to 6. Okay? And so that is what we need to evaluate. Now we can decompose that one more time. I'm going to go back here. We're going to decompose this sum into two pieces, where x2 is equal to x1, and then the sum where x2 starts at x1 plus 1 and goes up to 6. And so that's what we're doing here. So the reason we're doing this is because when x1 and x2 are equal, and they're both, one of the integers 1 through 6, then the PMF evaluates to 1 over 36, as we saw. When x2 is strictly greater than x1, then the PMF evaluates to 2 over 36. All right, so then we can evaluate this sum here. This is just 2 over 36 times 6 minus x1. And we can simplify this and we get the expression 13 minus 2 times x1 over 36. And so when we put that result together, we get the marginal PMF of x1 given by 13 minus 2x1 all over 36 for values of x1 in the space of x1, which again is the set of integers from 1 to 6, and the marginal PMF evaluates to 0 for any other value of x1. Now, this is a nice, concise expression for the marginal PMF of x1 that has this nice formula in it. But we can also express the marginal PMF in an expanded form in the following way. It's a piecewise defined function, as is this, but it's broken out in expanded form. And so it gives us the value associated with the marginal PMF for every value of x1 in its sample space. So it's equal to 1136 if we're evaluating the PMF, the marginal PMF at 1. If we evaluate this marginal PMF at 2, then it evaluates to 9 over 36. It evaluates to 7 over 36 if x1 is equal to 3, 5 over 36 if x1 is equal to 4, and so on. Now, this expanded form is obtained when computing the marginal PMF from a tabular representation of the joint PMF. And so if we look at, let's see here, let me bring this up. Here is a tabular representation of the joint PMF. And we've seen a similar table in a previous example. But what I've done is I've added margins at the top and on the right-hand side. So in the top margin here, I have computed the column totals. All right, so the sum of the joint probabilities in the first column, where corresponding to x1 equal to 1, that column total is 11 over 36. The column total corresponding to x1 equal to 2, the sum of the joint PMFs in this column, joint PMF values in this column, is 9 over 36, and so forth. The column total for this column, corresponding to x1 equal to 3, is 7 over 36. Corresponding to x1 equal to 4 is 5 over 36. The column total for x1 equal to 5 is 3 over 36. And then finally, the column total for x1 equal to 6 is 1 over 36. And these column totals give us the values of the marginal PMF of x1. And this is actually where the term marginal PMF comes from, because the PMF values are in the margin of this joint probability table. And so you see, these are the same values, and those values come directly, very easily from that joint PMF table. Now let's find the marginal CDF of x1. Now first, let's introduce some notation just to make sure we're all on the same page. So this notation here denotes the greatest integer function. In other words, when we evaluate this function at a particular real number x, then what it evaluates to is the greatest integer that is less than or equal to the argument. So for example, if we evaluate this at 3.5, then the greatest integer function at 3.5 is equal to 3, because 3 is the greatest integer less than or equal to 3.5. Evaluated at 4.2, the greatest integer less than or equal to 4.2 is 4, and so it evaluates to 4. If we evaluate it at 5, then the greatest integer less than or equal to 5 is 5. All right, and so that's what that would be. That's what that would evaluate to. So with that in mind, let's derive the marginal CDF of x1. Now denote the CDF of the marginal distribution of x1 by capital F sub 1. Since the space of x1 is the set of integers from 1 through 6, it follows, and again this is because you'll remember that the CDF is a probability accumulator. And so if we evaluate this probability accumulator at any value of x1 that is strictly less than the smallest value in the sample space of x1, then we know the amount of probability that we've accumulated is 0. So the CDF, the marginal CDF of x1, evaluates to 0 at any value of x1 that is less than 1. And if we evaluate it at any value of x that is greater than 6, which is the largest value in the sample space, then we know we've accumulated all the probability, and so it evaluates to 1. So we get those two for free, basically. We really don't have to do any calculation. We just need to understand what the definition of the CDF is and realize and remember that it's a probability accumulator. Now, for values of x1 between 1 and 6 inclusive, and notice that I'm saying for all real numbers, not just the integers, because remember that the CDF has to be defined at every real number on the real line. And actually, this is why we have to introduce and use this greatest integer function. Okay, so for values of, for real numbers, x1 greater than or equal to 1 and less than or equal to 6, the CDF evaluated at such a value of x1 is going to be the sum of the marginal PMF of x1, which we just found. We just found the expression for that. For values, we're evaluated at what we'll call k here, k going from 1 up to the greatest integer less than or equal to the argument x1. Okay, so then we know that over those set of values, this marginal PMF evaluates to the expression 13 minus 2k all over 36. Now I can pull the 1 over 36 out front, and when you go through and do the calculation, all right, then you see what we're getting here. And when you simplify, you get this expression, the greatest integer function evaluated at x1 times the quantity 12 minus the greatest integer function evaluated at x1, all of that over 36. And so when we put these three results together, we get the fully specified expression for the marginal CDF of x1 given here. So again, it evaluates to 0 if we evaluated at any value of x that is strictly less than 1. The marginal CDF of x1 evaluates to 1 for any value of x1 that is greater than 6. And then for any value of x1 greater than or equal to 1 and less than or equal to 6, it evaluates to this expression, the greatest integer function at x1, times 12 minus the greatest integer function at x1, all over 36. So that's again, that's a nice representation for this. It's fairly concise. It is a piecewise defined function, but it does have this nice expression here, which follows from the representation we had for the marginal PMF. Now we can also express the marginal CDF in expanded form in the following way. And so you see the values taken on by the marginal CDF for values of x, depending upon the intervals, the interval over which the value x1 resides. And this form of the marginal CDF follows very easily from the expanded form of the marginal PMF. All right, and let me also show you that, let's see here. Here is another table. Again, I've shown, I've got the joint PMF in the body of the table. I've got the values that x1 takes on down here, the values that x2 take on in the rows, and to the margins, I've added an additional set of margins for the marginal CDFs. So again, if we look up here at the top, and that's our focus right now because we're dealing with the marginal distribution of x1, then we see that the values taken on by the marginal CDF of x1, this probability accumulator, when evaluated at the values in the sample space of x1, we get 11 over 36, and then 20 over 36, and then when we get to 3, we've accumulated a total probability of 27 over 36. When we get to the point 4, we've accumulated an amount of probability equal to 32 over 36, and then 35 over 36, and then 1. And so that kind of representation, all right, which we can express more fully, more completely here, because remember, we have to specify the marginal, we have to specify the CDF so that it's defined at every real number. This kind of representation follows very easily from a tabular representation of the joint PMF. From that joint tabular representation of the joint PMF, we get the expanded form of the marginal PMF, and then from that we get the expanded version of the marginal CDF. Okay, now let's look at the marginal distribution of X2. And let's start off by finding the marginal PMF of X2. So again, we'll denote the marginal PMF as was described previously, the marginal PMF of X2, that is, by F sub 2. And note that the space of X2, which we'll denote by a script A sub X2, is again the set of integers from 1 through 6. Now the marginal PMF of X2, remember that to get a marginal PMF, and when we're dealing with discrete random variables, we sum the joint PMF over the variable that we're not interested in. So in this case, we're interested in X2, we're not interested in X1. So we're going to sum the joint PMF over the values of X1 in its sample space. And so that's what we're doing here. The marginal PMF of X2 at a particular value of X2 in its sample space is given by the sum, X1 going from 1 up to 6, of the joint PMF evaluated at each of these values of X1 and the given or specified value of X2. Now again, I'm going to decompose this sum into two pieces. The first being the sum of the values of the joint PMF, where X1 ranges from 1 up to X2. And then in the second term, the second summation, we're adding up the values of the joint PMF where X1 starts at X2 plus 1 and then goes up to 6. And the reason we're doing this is because over this range of values of X1, the joint PMF evaluates to 0, and so we're left with that piece there. All right, and then what we're going to do is we're going to take this piece that remains, and we're going to decompose it one more time. The first piece being the set of values, we're summing over the set of values of X1 from 1 up to X2 minus 1. So in this case, so over that range, X1 is strictly less than X2. And then the last term would be where X1 is equal to X2. And again, the reason we're doing this is because when we know that from the expression for the joint PMF of X1 and X2, when X1 and X2 are equal, then the joint PMF evaluates to 1 over 36. When X1 is strictly less than X2, it evaluates to 2 over, and this says 26, it should be 2 over 36. Be sure to correct that in your notes. Okay, so then we have to sum up this 2 over 36 this many times, and so what we get is 2 times the quantity x2 minus 1 all over 36. So we add it to the 1 over 36. And so we get this nice expression, 2 times x2 minus 1 all over 36. And so we put these results together, and we get the fully specified expression for the marginal PMF of x2. It's equal to 2 times x2 minus 1 over 36 for all values of x2 in the space of x2, and for any other value of x2, it's 0. Now again, we can express the marginal PMF in more expanded form, where we show the value taken on by the PMF at each value of x2. And this says x1, this should be x2. Copy and paste issues. Okay, so for when x2 is equal to 1, then the PMF evaluates to 1 over 36. When x2 is equal to 2, the PMF evaluates to 3 over 36, and so forth. And again, this is the form obtained when you obtain it directly when computing the marginal PMF from a tabular representation of the joint PMF. And so if we look at this table again, now we're interested in the marginal PMF of x2. And so the marginal PMF of x2 is going to be obtained, be given by the margin totals, the row totals here. Okay, and so the marginal PMF of x2 evaluated at 1 is 1 over 36. The marginal PMF of x2 evaluated at 2 is 3 over 36, and so forth. And so that is, it's a very natural way to obtain this more expanded version using that kind of a table. Either way is fine. You know, when we're working examples, it may be rather difficult in some situations to go through these kind of calculations and get this succinct representation that we've got here. So this is perfectly acceptable. So if you're doing a lab assignment where you have to find marginal PMFs, don't feel like you have to find an expression like this. This is a perfectly fine representation of a marginal PMF of a discrete random variable. Okay, then we want to find the CDF of the marginal distribution of x2, and so we'll denote it by f cap f sub 2. And since the space of x2 is the set of integers from 1 through 6, again, it follows that the marginal PMF of x2 is going to be 0 for any value of x that is strictly less than 1. It's going to be 1 for any value of x2 strictly greater than 6. For values of x2 between 1 and 6, inclusive, and again, we're not restricting ourselves just to the integers, for any real number greater than or equal to 1 and less than or equal to 6, then the marginal CDF of x2, evaluated at such a value of x2, is going to be given by the sum of the marginal PMF of x2, which we just found, evaluated at an argument that we'll call k going from 1 up to the greatest integer less than or equal to the argument x2. And over such values, we know that the marginal PMF evaluates to 2 times k minus 1 over 36. Okay? And then we can do some manipulations here. And it turns out that once we simplify, that the marginal CDF of x2 for values of x2 between 1 and 6 is equal to the square of the greatest integer less than or equal to x2 all over 36. And so when we put these results together, we get the fully specified expression for the marginal CDF of x2, and it's given by the following. When evaluated at a value of x2 that's strictly less than 1, we get 0. When evaluated at a real number between 1 and 6 inclusive, it evaluates to the square of the greatest integer less than or equal to that argument, all over 36. And if we evaluate it to a value greater than 6, then it evaluates to 1. Now, the marginal CDF of x2 can also be represented in this expanded form, just like we did with the expanded form for the marginal CDF of x1. And so you see here that this function is defined for every real number. And it follows from a tabular representation of the joint PMF. So the joint PMF is here in the body of the table. And again, we're interested in the marginal PMF of x2 now. And so over here in the rows, row totals, we have the marginal PMF in these cells. And then we accumulate those cells as x2 increases. And so this is where we get the values for the marginal CDF. And again, the reason we call them marginal PMFs and marginal CDFs, marginal distributions, is because these probability values are obtained in the margins of the joint probability table. Okay, so to just put everything together, here are the marginal PMF and CDF of x1, and then we have the marginal PMF and CDF of x2. Now, the example also asks us to find, for each of x1 and x2, to find the mean, the variance, the skewness, and the kurtosis of the marginal distribution of x1, and to do the same for the marginal distribution of x2. Now, you have, we've already done that. We've done examples doing that, so you know how to do it. What I wanted to focus on in this particular lecture in going over this example is how to find the marginal PMF and CDF, because that's what's new at this particular point in time. So you have representations for the, let's see here, the marginal PMF of x2, as well as the marginal PMF of x1. And so what I would recommend is to use the spreadsheet that you have constructed, the spreadsheet template that you have constructed and are using to find these various distributional characteristics of discrete random variables. All you'll have to do is make sure that you have places for the sample space, enough rows for the sample space in your spreadsheet, and then enter in the corresponding probabilities. And so you'll be able to create two spreadsheets from the template. Have one spreadsheet for the for the marginal PMF, the marginal distribution of x1, and then another spreadsheet for the marginal PMF of x2, and you should be able to calculate the mean, the variance, the skewness, and the kurtosis for each one of those distributions. In fact, let's just do that. So I've got my template brought up here, and I've got the exact values for the sample space that I need. I've got the correct number of rows, and so let's see. This is going to be the marginal PMF of x1. So example 48, marginal PMF of x1. All right, and I'm not going to bother changing x to x1. That's not necessary. And so then I just type in the probabilities here. So 11 over 36, and then 9 over 36, and then 7 over 36. Then we have 5 over 36, and then 3 over 36, and then 1 over 36. Okay, and so then all I had to do is type in, I need to make sure that I've got the sample space in correctly, type in the probabilities, all right, and you can see here, you can see up here, all right, it's showing me the actual fractions that I entered in. All right, it's showing me the decimal representation in the cells. Okay, so I've got those entered correctly, and now everything else is all, programmed in. Everything else is these cells have formulas in them, and so then I get the values down here that I need. So the mean of the mean of the marginal distribution of x1 is 2.5278. The variance is 1.9715. The skewness is 0.6356, and the kurtosis is 2.4435. All right, and so we can do a very similar thing for the distribution of x2. Okay, so there we go. Opened up another copy of the template, and this is example 48. This is marginal PMF of x2. Sample space is correct. Now I just need to enter the probabilities. In this case, it's 1 over 36, and then 3 over 36, and then 5 over 36, and then 7 over 36, and then 9 over 36, and finally 11 over 36. Okay? And so when we get this, when we enter those values, then everything is automatically calculated. The mean of this distribution is 4.4722. The variance is 1.9715. The skewness is negative 0.6356, and the kurtosis of the marginal distribution of x2 is 2.4435. So that is how I would recommend working through an example like this. For this situation, we could do some more mathematics and use formulas, to derive the formulas for our expressions, derive these values from the marginal PMF and do it mathematically. But it hardly seems worth it because this is not a general problem. This is a very specific problem. All right, we know that the values that the two dice can take on are 1 through 6, and that the minimum and maximum values, we know those are not going to change. So there's really no benefit to doing it in any more generality than what we're doing it here with these spreadsheets. So anyway, this is all we're going to do on this example. You can go ahead and plot the PMF and CDF as well. I'm not going to bother with that because we've seen that kind of thing in other lectures. So I'll stop this particular video. We have some more examples involving continuous random variables that we will look at in the next lecture video.